Shown in the figure below is a set of equipotential lines that were created by some set of point charges. The lines represent potentials ranging from minus 300 volts on the left to plus 300 volts on the right in steps of 100 volts. Also labeled in the plot are 3 points, A at 0, 0, B at 1.5, 3 meters, and C at 3 meters, 2.5. We're then asked a series of questions. This problem is going to allow us to exercise our understanding of the relationships between potential and electric field. You'll remember that because potential is analogous to potential energy, and field is analogous to force, the relationship that exists between them is an integral of field produces a difference in potential. This is identically analogous to a relationship we had last semester. That relationship harkens all the way back to the concepts of work and energy. Work is, of course, force times distance, and when we promoted the concept of work for conservative forces to be instead represented as differences in potential energies, we wound up introducing a minus sign when we moved the work to the energy side of the equation. That relationship continues to hold between potential and field because, as we remember, potential is potential energy per unit charge and field is force per unit charge. Clearly, if differences in potential are the integral of field, then field is the derivative of potential. In writing these relationships, we have performed a small mathematical sleight of hand. Electric field is a vector, and so it has 3 components. However, potential is a scalar. For this reason, each of the 3 components, for example, the x component, is related only to the x derivative of potential. The y component of electric field is related only to the y derivative of potential, and the z component of electric field is related only to the z. Remembering which way around we treat the derivatives versus the integral is as simple as understanding the units. Potential is measured in volts, change in position is measured in meters, and of course electric field is measured in volts per meter. Finally, the last part of this relationship that we need to understand regards the minus sign. This minus sign implies that electric field will always point downhill. And by downhill, we mean that the electric field points from the region of highest potential towards the region of lowest potential. In part A of the problem, we are to select which point A, point B, or point C, has the highest electric field. Based upon our relationship, the electric field is largest where the derivative or rate of change of the potential is the largest. If you imagine the lines as a contour graph showing potential as being height, you can see that wherever the lines are closely spaced to one another, the potential varies rapidly as you move from one location to the next. So wherever the potential lines are bunched closely, that is the region where the electric field is largest. And clearly, that is at point A. Next, we're asked which point on this diagram has the lowest electric field, and that will be the point where the equipotential lines are spaced by the largest amount, and that's point C. Next, we are asked to estimate the strength of the electric field at a point halfway in between B and C. A key word in this question is the word estimate. That means our calculation does not need to be exact. We don't need to take an actual derivative, but instead we will allow ourselves to approximate the electric field simply by taking a difference in potential divided by a difference in position. In order to make this calculation, let's look closely at the 2 points B and C and recognize that the distance between them is given by this straight line. We further remember that we've been given the coordinates of each of these 2 points. Point C is located at 3 meters, 2.5 meters, and point B has x and y coordinates of 1.5 and 3 meters respectively. If we draw a right-hand triangle, we can then recognize that the sides of this triangle have known lengths. The base of this triangle is of length 3 minus 1.5, which is 1.5 meters. And the height of this triangle is 3 minus 2.5, which is 0.5 meters. Then, by the Pythagorean theorem, we can see that the hypotenuse length is the square root of the sum of the squares of the 2 sides, and this gives us an answer of 1.58 meters. Looking back to the original figure, we see that point C lies along a line whose potential is 300 volts. And since we were originally told that each of these equipotential lines is 100 volt different than the previous, point B clearly lies along a line whose potential is 200 volts. Therefore, the numerator in our electric field calculation, delta V, is the difference between 300 volts and 200 volts, which is 100 volts. In this case, we're ready to calculate the electric field at the point midway between these two by taking the 100 volts and dividing it by the 1.58 meters, yielding an electric field of 63.25 volt per meter. Part D asks us to draw roughly 6 electric field lines on top of the previous figure. In order to do that, we have to respect the minus sign in our derivative calculation, which tells us that the electric field will always run downhill. Clearly, all points along an equipotential line have the same potential as one another, and therefore if we were to follow this line, we would neither be going uphill nor downhill. Downhill will always be defined as being perpendicular to the equipotential line. And so for that reason, our task in drawing electric field lines is to make a curve that intersects each one of our equipotentials in a manner that is perpendicular to that line and that overall points downhill. My artistic talent is not particularly large, and I don't expect any better from my students. But I would expect that any student who was asked to perform a drawing like this on an exam would take care to make sure that, number one, the electric field points downhill, that respects the minus sign in the derivative, and number two, some attempt is made to recognize that the electric field lines should be roughly perpendicular to the best of your artistic ability to the equipotential lines. And finally, in part E of the problem, we've been asked the simple question that if these lines were generated by 2 point charges, one of them on the left and the other on the right, determine which side of the graph contains which charge. Going back and inspecting the graph, we recognize that electric field lines run from positive charges toward negative charges. Therefore, the answer is simple. The positive charge must be located near the source of these lines on the right, and the negative charge must be located at the destination of these lines on the left. And this completes our graphical understanding of the relationship between electric field and electric potential.